Good morning. So today we will be solving a problem on centrifugal pumps, right? So till now we have solved problems on the turbines. Now we will solve a problem on the centrifugal pump. It goes like the impeller of a centrifugal pump has an outer diameter of 1.5 meter. It lifts water at a rate of 2000 kg per second. The blade is making an angle 145 degree with the direction of motion at outlet and the speed being 300 rpm. Radial velocity of flow is 3 meter per second. So find the power required to drive the impeller. This is the problem given. Now we need to observe certain things here. Now we need to observe what kind of a machine centrifugal pump is. A centrifugal pump is a machine in which the energy from the mechanical part is being converted into fluid energy. Understood? And we should always remember that in a centrifugal pump, fluid always enters radially. Okay, it is a radial machine. You should remember, as I told you previously itself, Vf, the flow velocity, can be called as axial velocity in axial machines, and it can be called as radial velocity in case of radial machines. Since this is a radial machine, here he has given us radial velocity of flow is 3 meter per second. So that is why this data is Vf, right? So now, when, as I told you, when the fluid enters radially, V1 becomes equal to Vf1. So that is why inlet triangle gets modified like this, and the outlet triangle remains same. And let us look at the data that are given here. So now we know that he says the outer diameter is 1.5 meter. That means in the pump the fluid enters at one radius and it is leaving at another radius. So here outer diameter is given, that therefore D2 is equal to 1.5 meter. Then he says the water is getting pumped at 2000 kg per second, and that is our mass flow rate, m dash, 2000 kg per second. Then he says the blade is making an angle 145 degree with the direction of motion, right? And that is why it is beta 2 dash. We will explain about this beta 2 dash while explaining the triangle. Then he says the speed of the wheel is 300 rpm, that is given, fine. Then the flow velocity, which is equal in both the inlet and outlets, is 3 meter per second, right? This is the data given. Now what is he trying to ask us? He is asking us to find out the power of the machine, isn't it? So let me explain the triangles now. See here, as I told you, since the entry is radial, the inlet triangle gets modified like this. Coming to the outlet triangle, in the outlet triangle, look at the direction of the U2 here. Okay, now the direction of U2 is towards the right, and with this direction, in the direction of motion, if you measure the angle beta 2, it is 145 degree. Okay, so this is beta 2 dash. But what is the angle of VR2? VR2 angle is beta 2. So now from the triangle, if you can make out here, so beta 2 is total 180 minus this angle, 180 minus 145, which is 35 degree. Okay, so the direction is opposite, right? He says with the direction. So with the direction it is 145 and actual beta 2 is 35 degree. Hope you have understood, right? So you should always understand the sentences properly and then connect it to the triangles here. So we got beta 2 here. Beta 2 is, so now, therefore beta 2 is 180 minus beta 2 dash, which is 145, beta 2 is 35. Now coming to the actual question, the power is asked. We know the formula for power already. It is m dash by Gc into U1 Vu1 minus U2 Vu2. That is the actual formula that we remember. But since this is a power absorbing machine, it becomes U2 Vu2 minus U1 Vu1. But if you observe the triangle here, Vu1 is already 0, right? Since the entry is radial, Vu1 is already 0. The second term becomes 0, and that is why power is m dash by Gc into U2 Vu2, right? So how do we calculate U2 then? We know the diameter and we also know the speed of the rotor. So that is why it is pi d2n divided by 60 at the outlet. So it becomes 23.56 meter per second. That is the value of blade speed at the outlet. Right? Next, not the blade speed but the rotor speed. From the outlet velocity triangle, we can say Vu2 is equal to U2 plus Vf cot beta 2. Right? What is this Vf cot beta 2? See here, Vu2 is U2 plus Vf cot beta 2. Right? So now, coming to that, U2 we have already calculated. Now, Vf is given as 3 and cot 35. So now, taking cot theta is equal to adjacent by opposite. Right? So it is the inverse of the tan. Right? Now it becomes Vu2 becomes 27.84 meter per second. So now, substituting U2 and Vu2 in the power formula, we will get P is equal to mass flow rate is given as 2000 kg per second divided by Gc 1000 into 23.56 into 27.84, which are the values of U2 and Vu2. We will get 1311 kilowatt. So that is the power required to drive this pump. If you have not understood this value Vf cot beta 2, let me explain with the help of this triangle. Vf cot beta 2 is this part. Okay, let me call it x. Right? What is Vu2? Vu2 is U2 plus x and x is Vf cot beta 2. Okay. Since we know the angle beta 2, with this help you can calculate x value. Got it? And that is the problem. Let us move to the next problem, which is a proof kind of problem. Okay. See, these kind of proofs are generally asked. Right. So show that epsilon max, epsilon is utilization factor, show that epsilon max of an axial flow turbine with degree of reaction as 0.25, that is 1 by 4. The relationship between the blade speed U to the absolute velocity at rotor inlet V1 should be U by V1 is equal to 2 by 3 cos alpha 1, where alpha 1 is the nozzle angle at inlet. We should assume that the flow velocity is constant throughout. Again, this is a proof kind of problem. Here we are given with an axial flow turbine, right, in which we have been specified a certain degree of reaction which is 0.25, and we need to show and we need to prove that the relationship between blade speed U and absolute velocity at inlet V1 as U by V1 is equal to 2 by 3 cos alpha 1. These three are related, and this is known as speed ratio. If you will come across this in coming chapters, this is U by V1 is known as speed ratio. This we have to prove. Now what is given in this problem? In this statement we are told that this is an axial flow machine, right? So U1 is equal to U2 is equal to U. Then he says that R for this machine is 0.25, or in other terms it can also be written as 1 by 4. And he also says at the end that the flow velocity is constant throughout. That means inlet and at outlet Vf is same. Vf1 is equal to Vf2 is equal to Vf. Right? Then he says epsilon is maximum. What is the condition that we need to assume here for the maximum utilization factor? So when epsilon becomes epsilon max, we know that V2 should be axial. Right? So that means there should be minimum loss. When there will be minimum loss? When V2 will be axial. When V2 becomes axial, V2 becomes equal to Vf2, and when V2 becomes equal to Vf2, VO2 becomes 0, right? And that is how we can draw with this condition we should draw the outlet triangle, right? So now I have drawn the inlet and outlet triangle combinedly, since we know two conditions. Because the flow velocity is constant, so I have made that as the common line. This is the common line Vf1 is equal to Vf2 is equal to V2 here. Okay, at the outlet Vf2 is equal to V2. So triangle ADE is my outlet triangle, triangle ABD is my inlet triangle. So even if you draw, if you draw separately also, this is fine, that is fine. But just for the proof purpose, I have drawn combined triangles. We will use that within the proof. Okay. So now, I hope you are clear with the triangle. Triangle ABD is the inlet triangle. Triangle ADE is the outlet triangle. So I have just marked the VR1 tip as C here. So ABCD, triangle ACD is also a right angle triangle in which the CD is known as X. So what is VU1? According to this triangle, it is U plus X, right? So hope you are clear with that. Now let us move to the proof part. Okay. So now considering the triangle ADE, which is that the outlet triangle ADE, considering the triangle ADE, let me write VR2 square is equal to U2 square, U square plus V2 square, isn't it? So in the outlet triangle, VR2 square is equal to U2 square plus V2 square. So I shall not say U2 because U2 is U itself, right? So now, but what is V2? V2 is also equal to VF2, right? Which is equal to Vf. So let me write U2 square is equal to Vf square. Is that clear? Right? So now, let me modify that. V2 square equal to, this becomes U2 square or U square plus, what is V2? V2 is equal to Vf, isn't it? But what is Vf? This Vf, according to triangle ABD, okay, it is V1 sin alpha 1, right? So if I can consider this triangle ABD, the side AD is V1 sin alpha 1, right, which is Vf. So Vf is equal to V1 sin alpha 1. That is what I have substituted for Vf here. Understood? So let this be equation number 1. What is it? VR2 square is equal to U2 square plus V1 square sin alpha 1, or U square plus V1 square sin alpha 1. Let that be equation number 1, right? So next, proceeding to the next step, which is considering the triangle ABD, which itself is the inlet velocity triangle. What is VU1? VU1 is, obviously we know that V1 cos alpha, right? According to the triangle rules, it is V1 cos alpha. So, but what is VU1? As I told you, it is U plus X, isn't it? VU1 is U plus X. So let me modify this. So that is why, what is X now? X is V1 cos alpha 1 minus U. Isn't it? X is V1 cos alpha 1 minus U. So let this be equation number 2. Now, going for the further modification and considering the triangle ACD. Which is the triangle ACD? This is the triangle ACD. In this triangle ACD, from the Pythagoras theorem, I shall write VR1 square is equal to X square plus V2 square, right? This is the triangle. VR1 square, hypotenuse square, is equal to X square plus V2 square, isn't it? Or Vf square, right? Because V2 and Vf are same. Now, what is X here? X is V1 cos alpha 1 minus U, right? What is V1 cos alpha 1? V1 cos alpha 1 is VU1 minus U. X is VU1 minus U, right? VU1 I have written as V1 cos alpha 1 minus U whole square plus, what is V2? V2 is equal to Vf. Vf is equal to V1 sin alpha 1. The previous step, we have made that, right? Clear, right? So, now, V1 cos alpha 1 minus U whole square plus V1 sin alpha 1 whole square. Clear? Now, again, modifying that or simplifying that, VR1 square is equal to, now, let me take this out. So, it becomes A minus B whole square, A square, V1 square cos square alpha 1 plus B square, U square minus 2 into V1 into cos alpha 1 into U, right? Plus, as it is V1 square into sin square alpha 1. So let this be my third equation, equation number 3. Now, considering the definition of the degree of reaction, which we know, what is degree of reaction? It is the ratio of static energy divided by the total energy, isn't it? So, here the value given is 1 by 4. So, keep it as it is. Now, considering the formula, I shall write VR2 square minus VR1 square plus U2 square minus U1 square, right? But, sorry, U1 square minus U2 square, but since U1 and U2 are same, I shall not write that term here. So, that term is eliminated. U1 square minus U2 square term cannot be written because it will become 0. So, static energy becomes only VR2 square minus VR1 square divided by V1 square minus V2 square plus VR2 square minus VR1 square, right? So this is the, from the definition of what do you say, the degree of reaction, I shall write this formula directly. Now I know the value also, 1 by 4. Now modifying this. So taking 4 on that side and getting the denominator into the opposite numerator. So I shall write 4 into VR2 square minus VR1 square should be equal to V1 square minus V2 square plus VR2 square minus V1 square as it is. Right? So now getting this, the term into this side. So it becomes 4 VR square minus VR1 square minus 1 VR square minus VR1 square. 4 minus 1 is 3. So it becomes 3 into VR square minus VR1 square. V2 square minus VR1 square should be equal to V1 square minus V2 square. But now substitute the VR2 square value and VR1 square value, that is equation number 1 and 3 in the equation number 4. Right? So substituting equation 1 and 3 in equation 4, let me get, so the RHS remains same. What is it? It is V1 square minus V2 square. Now coming to the RHS, it is 3 into which value? VR2 square value. What is VR2 square value? U2 square plus V1 square sin square alpha 1 minus 3 into VR1 square value. V1 square cos square alpha 1 plus U square minus 2V1 U cos alpha 1 plus V1 square sin square alpha 1. Right? So after the substitution it will become like this. So now, so I will not write the LHS again. LHS is equal to V1 square minus, what is V2? V2 is equal to Vf. Vf is V1 sin alpha 1. So squared is V1 square sin square alpha 1. Right? So let me take V1 outside here. So it becomes 1 minus sin square alpha 1. But we all know 1 minus sin square alpha 1 is cos square alpha 1, because sin square plus cos square theta is equal to 1. Right? So what is the RHS becomes V1 square into cos square alpha 1. Right? So I have simplified the RHS now. Now coming to the LHS. So in the LHS, if you multiply here, this becomes 3u square. So here also it is 3u square, right? But it is minus 3u square, plus 3u square minus 3u square cancelled, and then it is 3v1 square sin square alpha 1. Here also it is minus 3v1 square sin square alpha 1. Both terms get cancelled. So what remains is 6u into v1 cos alpha 1, right? 6u into v1 cos alpha 1 minus 3 into v1 square cos square alpha 1, right? Isn't it? 6u1 cos alpha 1 minus 3v1 square cos square alpha 1 should be equal to v1 square cos square alpha 1, which is the RHS. So now I will take v1 cos alpha 1 as common and cancel it on both sides, because on both sides that is common. So what remains on the RHS? v1 cos alpha 1 remains, and v1 cos alpha 1 is taken common. Then on the LHS, what remains? 6u minus 3v1 cos alpha 1, right? Now let me modify a little bit. So I will take this into that side. So minus 3v1 cos alpha 1 becomes plus 3v1 cos alpha 1. So 3 plus 1 becomes 4v1 cos alpha 1 on the RHS. So what remains here? 6u, right? So what do I need? I need u by v1 ratio. So what do? I will just modify u by v1. So u by v1 equals to 4 by 6 cos alpha 1, right? 4 by 6 is 2 by 3. U by v1, that is the speed ratio, is 2 by 3 cos alpha 1. So this is the proof for this one.